Assalamu alaikum. Welcome to the second lecture of chapter 3 on elastic plastic fracture mechanics. We will of course start with a review of the previous lecture, and today the topics we will cover, we will continue with the hinge model for CTOD that we started last time. Then we will talk of the J contour integral, non-linear energy release rate, and probably, given time, lab measurement of J. So let us go through what we did in lecture 1 of this. We introduced elastic plastic fracture mechanics, EPFM, telling you that the two main new quantities that we will introduce are CTOD and J contour. Then we started talking of the crack tip opening displacement, CTOD, with the tests and so on performed by Well. We defined that the crack enlarges and this delta is the crack tip opening OD. We gave you the different derivations and so on, not the derivations but the final equations of how to deal with the CTOD in terms of the plastic zone correction. The figure where we are explaining the plastic zone correction RY and UY, and twice of UY is the CTOD. So we are continuing with that. We finally come up with equations for CTOD in terms of K1 and in terms of G, the stress intensity and the energy release rate. We continue now with the strip yield model, and we try to develop it again, Irwin correction, then strip yield model correction, and defining delta in both. We are showing the strip yield model and delta in comparison with that, and the equation. And we are now giving you two different geometrical definitions of how to define delta as the diameter of a semicircle or as a 90-degree intercept. Then we talk of laboratory measurement of CTOD, and we talk of the hinge model and so on, talk of the path. We remind ourselves of the SENT, which is not required, but the SEB, the single edge notch bend specimen, which we used for this measurement. We give you this hinge model, that delta, small delta, is what you have to find out, but you don't want to put the gauge inside, so you very easily measure this V, and then from similar triangles here you find an equation for the actual value of delta under a load P, of course, and the width of the specimen. So, and finally we showed you this diagram of variation between load and the crack mouth opening displacement or crack tip displacement and so on, that it behaves almost in the shape of a stress strain diagram, right, and so on. So here is where we stopped last time. So let us start today's lecture. I will go back to this figure so that you are mentally right here in the lecture rather than trying to remember, right? So this is it, that there is a specimen, and there is a notch and so on. There is, we have already cut, so that is the crack, so the crack size is there, and 3-point bending, 1 point, 2 point, 3-point bending is happening. W is the width of the system, and delta is the crack tip open, right? Once we bend it, once we open it, then the crack is opening and we want to find delta. Earlier there was something called a plug gauge which was sent inside to measure this one, but this was rather inaccurate and so on. So they said that this measurement of how much opening has been happening here is much easier. So by the gauge we measure only this, and by then this A and RW minus A and so on, we define an equation so that we can find delta from there, right? So this is the hinge model. This is what we were describing. So the figure we have just shown you, and then the other figure which we will just show you about the stress strain type of diagram. So at any given point on the curve, displacement is separated into the elastic and plastic components by constructing a line parallel to the elastic loading line, just like we do in a stress strain diagram, So we do the measurements, as the load increases, then the crack tip opening is increasing. Initially it behaves in an elastic manner, then it becomes plastic. So at any point in the plastic region, if you drop a straight line here, then it is the total crack mouth opening, right? Total. But if you draw a parallel line to this initial one, then this much is the plastic part, and that much from here till the straight line, that would be the elastic part. So we are not concerned about the elastic part, because elastic part is totally covered by LEFM, linear elastic fracture mechanics. So the main thing is the plastic part. That is why we are drawing this curve, that if this curve is there, then at any point we can draw a line parallel to the initial straight line and measure from 0 to this line, and we are getting the V plastic, right? So this is there, that from there you are measuring total V in the hinge model, and you are separating the plastic part of it, just that, right? So now CTOD in this specimen is estimated by delta. The CTOD delta is delta elastic plus delta plastic, as we just showed you. The delta elastic is totally covered, right? If it is, we just did the previous section, K1 squared by M sigma by S E dash. This E dash is equal to E for plane stress, and it is equal to the other one for plane strain. So this equation, because we already have it, so this is the elastic portion of it, and the plastic portion is from here. The plastic portion is from here, where now V is not total V, it is only the V plastic. So R plastic, V plastic, W minus A, and so on, right? So elastic and plastic subscripts denote the elastic and plastic components. Now the experimental work, of course, will be very tough. I mean, it is not done in every laboratory. It is not done in many universities in the world. It is not available in SQU. But we at least know the technique. So in the laboratories where this type of 3-point bending is done and where all the measurements can be recorded, okay, we can do that. The elastic stress intensity factor is computed by inserting load and specimen dimensions into the approximate expression in table 2.4. Table 2.4, you remember from the previous chapter table, it was just that table where the value of FW by A was given for different types of specimens, SENT, SEB, and so on. So that is table 2.4, remember. Plastic rotation factor RP. Plastic rotation factor RP is approximately 0.44 for typical materials and test specimens. Now this again, if we are in a full course on fracture mechanics at a higher level, we will have access to books or handbooks or tables for the value of RP. If we go to later chapters in Anderson, we will have more of it. But for typical materials and test specimens, general RP is 0.44. Note, the equation reduces to small scale yielding result for linear elastic conditions, but the hinge model dominates when V is mostly plastic. Remember, if the linear elastic conditions are there, then this portion will go away. This portion will go away. So the total delta will be the delta that we derived earlier. But in general, if it is a metal and metals have good plasticity and so on, at least significant plasticity, then this portion will be much larger than this portion. This portion will be much larger than this portion. So what they are saying is that we measure the total V in the hinge model, but in that total V, the V elastic is very small and V plastic is very large. It is just like a strains. If you see in any stress strain diagram, the strain at the end of the elastic region is very small, 0.02%. Remember, the yield point is defined as 0.02. So 0.02%, which means actually 0.002 and so on, right? So it's a very small compared to, even if you go to 0.1 strain, 0.1 strain in the plastic region, then 0.002 is a very small fraction. So the same thing here, that the V, the crack tip opening, because of the elastic region is very small and the V plastic is much bigger. Details of CTOD testing are given in chapter 7, which we are not covering in this course, but you know that you have the book, you know the book now. So in the future, if anybody ends up in a company where fracture mechanics is being practiced, then in chapter 7, details of CTOD testing are available. And chapter 9 outlines how CTOD is used in design, that if you are designing, manufacturing and so on, then how do you use the CTOD information? That is in chapter 9. I keep on doing this so that yes, we are in an introductory course, we are in an undergraduate system, so we are not touching all the higher details. The book is very big, it's a comprehensive book on fracture mechanics, so some portions of the book we are not going to cover. But you know that if I want to do CTOD testing in detail, then I can find it in chapter 7. If I want to apply the concept of CTOD in design and how to improve design and so on, then I go to chapter 9. So here it is not from our book, from internet sources and so on. I am just showing you the typical test arrangement, sample geometry and measurement technique for CTOD testing. Right, so this is the standard test specimen, the dimensions, the crack, right, and so on. The other view, so that you know the thickness of the piece and the width is roughly twice of the thickness and so on. This is the standard specimen. And then we have two views of the same thing, that this is the general thing, the 3-point bending, and there is a clip gauge. There is a clip gauge. It is a type of gauge which measures distance. So now it is only here, it does not need to go inside, right? So it is only here, it measures only this much, and right, and it is a 3-point bending system and so on. And we are again, right, that accurately positions knife edges so that you know exactly how much displacement is there, the test piece is there, the total crack length is there and so on. So the initial crack and the opening. So this is the schematic diagram of how CTOD testing is actually done. If the system is there in a lab, then they will have an exact notched specimen, which is difficult to get manufactured except in methods like electric discharge machining, EDM and so on. So you have to have that specimen, you have to have the 3-point bend system, and you have to have very accurate clip gauges which are directly connected to your computer and so on, so you can keep on recording the opening as it goes, right? So that was that. I mean, we were talking of CTOD. Remember, CTOD and J integral are like K1 and G. When linear elastic fracture mechanics was there, then the whole fracture mechanics was described by two major factors where you could find the fracture toughness of the material, either K1C or GC. So K1 is the stress intensity in mode 1 and G is the energy release rate. So now in elastic plastic fracture mechanics, one quantity that will describe this elastic plastic fracture mechanics will be the crack tip opening displacement CTOD or delta, and the other will be the J contour integral. So we have finished the introduction to CTOD, and now we are trying to cover J contour integral. The J contour integral has enjoyed great success as a fracture characterizing parameter for non-linear materials. So compared to CTOD, which was very simple, this is more successful as a measure. Rice, it is a scientist, engineer, he idealized elastic plastic deformation as non-linear elastic. This is a major thing. Remember, in one of the last lectures, we tried to ask you, and then we summarized different types of material models: perfectly elastic, elastic perfectly plastic, elastic linear strain hardening, elastic non-linear strain hardening, right, and piecewise strain hardening. So here that it is elastic plastic, but to get a good mathematical foundation which is simple, he said, I will assume it is non-linear elastic. So the curve is there, but it is elastic in assumption that everything can go back to zero deformation. So you are taking a normal elastic plastic curve, as in a stress or strain and so on, normal elastic plastic curve. You are assuming one extra thing, that you don't have to go back on a straight line parallel to the initial straight line, you go back entirely on the same curve. This is called non-linear elastic. Rubbers and polymers are like this. So we are saying that we will take all the calculations which are there for the metal, but assume a non-linear elastic behavior.